Hello, I'm going to present a new contributions to neuromorphic engineering in Wetware. It refers to the discrimination of acoustic frequencies through their effects on chemical waves. Chemical waves are autocatalytic reactions propagating through excitable media. For instance, an action potential is an electrochemical wave propagating along the axon of a neuron. And electrochemical waves propagate in the form of spindles in our cerebral cortex to consolidate and integrate memories during our sleep. The Belousov-Zhabotinsky reaction can give rise to wonderful examples of chemical waves. In this accelerated video, you can see spontaneous phase waves generated from the periphery of the dish and moving towards the center, but also you can see target patterns, and they can be either sparse or dense. Since the behavior of the Bézier reaction is strongly affected by mixing, we explore the response of its chemical waves to mechanical oscillations. These pictures present the experimental setup we used in our experiments. On a polystyrene Petri dish, we poured a thin layer of the Bézier reaction, and we subjected this thin layer of the solutions to vertical vibration with frequencies in the range of the acoustic waves. Based on the response of the Bézier reaction, we can discriminate 7 acoustic bands in the range 10 to 1000 Hz. Here, I show the behavior of the Bézier reaction when it is unperturbed. What happens when we apply frequency in the range 2600 Hz? We still see spontaneous phase waves and target patterns, but the front waves of the target patterns are not circular. They are more irregular due to the mechanical waves. What happens if we apply frequencies in the range 650 and 500 Hz? We start to see a pacemaker of advection-induced phase wave in the center of the dish. These advection-induced phase waves propagate anisotropically towards the periphery of the dish. A clover-type shape is formed, and simultaneously, spontaneous phase wave and target patterns are generated in the periphery of the dish. What happens if you apply frequencies in the range 500 and 2000 Hz? We start to see a portion of the solution, an annulus part of the solutions, vibrating spontaneously. And advection-induced phase waves are generated in this part of the solutions. They move towards the center, and finally, they spread in the rest of the solution. What happens if we apply frequencies in the range 2095 Hz? 2 regions of the solution appear vibrating, one in the center and one in the periphery, separated by an annulus nodal region. The advection-induced phase waves are generated in one point of the periphery of the dish. They engulf the nodal region, they cross the central region, and finally they reach the opposite side of the dish. What happens if we apply frequencies in the range 95 and 50 Hz? We start to see Faraday patterns generated by transverse standing waves. The Faraday patterns in this 5th range are asymmetric. The amplitude of the oscillations are more pronounced in the periphery rather than in the center. And the advection-induced phase waves are generated in the center, and they move radially towards the periphery of the dish. What happens if we apply frequencies in the range 50 and 15 Hz? Well, the Faraday patterns are now uniform, and the dimensions of the cell constituting the Faraday patterns increase by lowering the acoustic frequency. Advection-induced phase waves are generated in one point of the periphery of the dish that is unpredictable, and they move quite quickly towards the opposite side of the solution, sweeping the entire solutions. And finally, what happens if we apply frequencies in the range 15-10 Hz? The dimensions of the cells constituting the Faraday patterns are so large they fragment the front waves of the advection-induced phase wave that appear quite irregular. The velocity of the advection-induced phase wave is clearly dependent on the acoustic frequency. The lower the frequency, the faster the propagation of the advection-induced phase wave. And the interpretation of this dependence was possible by invoking the networks of cells model. The solutions of the Phys reaction is described as a network of open reactors of cells communicating chemically through the exchange of reagents by diffusion and advection. The acoustic frequencies affect the chemical coupling between these micrometric cells, and the lower acoustic frequencies guarantee a more extended chemical coupling, the formation of larger clusters, and hence a faster propagation of the advection-induced phase wave. We reproduce quite well the dependence, the experimental dependence of the advection-induced phase wave velocity on the acoustic frequency. 3 are the key outputs for discriminating the 7 bands in the 10 to 1000 Hz range. One key output is the spatiotemporal pattern generated by the different acoustic frequencies, and it might be constituted by advection-induced phase wave, spontaneous phase waves, and target patterns that can be either sparse or dense. The frequencies of these chemical waves are from 3 to 5 orders of magnitude smaller than the acoustic frequencies. The second key output is the dependence of the advection-induced phase wave velocity on the acoustic frequency. That is describable through this polyexponential function. And finally, the third key output is the dependence of the Faraday wave's wavelength on the acoustic frequency. The lower the frequency, the larger are the dimensions of the cells constituting the Faraday patterns. Similarly to the human ear, wherein the cochlea is a transducer of mechanical energy into electrochemical energy, and it offers topographic representation of the acoustic waves along the asymmetric basilar membrane, our bioinspired Chemo-Acoustic system, based on the Belousov-Zhabotinsky reaction, is a transducer of mechanical energy into chemical energy, and it offers peculiar spatiotemporal patterns as representation of different acoustic bandwidths. I hope you enjoy reading our paper, where we demonstrate that chemical waves can indeed dance. Thanks for your attention.